Our next speaker is Brandon Chalifoux, and this talk is Flex Modules, a path to high-resolution X-ray telescope optics via final step figuring.
All right. Thank you. This is my first time at the Space Institute Symposium, and I'm happy to be here. So I'm an assistant professor here in the College of Optical Sciences. And today I'm going to tell you about a technology development effort aimed at providing a potential solution to a decades-old problem, which is how do we build the optics for a high-resolution, high-throughput, flagship class X-ray telescope? We have a large number of student contributors and professional contributors here at the U of A, primarily in the College of Optical Sciences, as well as collaborators at NASA. We've had funding from NASA, College of Optical Sciences, TRIF, et cetera, for some of the aspects of this. So I want to start with why do we care about X-ray telescopes? Astronomers want to observe things in highly energetic processes in the universe. And the series of images of the Crab Nebula provided by NASA, taken over a wide range of wavebands, highlights the fact that in the lower right corner, this is the X-ray image from Chandra X-ray Observatory. This is the only image where you can actually see the core of the neutron star that's in this at the center of this nebula here. And so X-ray telescopes enable you to see these highly energetic processes. But I'm not an astronomer, I'm a technologist. I'm interested in the optics. And so what makes X-ray telescopes hard is really fundamentally that you only get efficient broadband reflection off of surfaces in the X-ray band, whether it's soft X-ray or hard X-ray, near grazing incidents. Grazing angles are typically a degree or often much less than that. So the telescopes often have these grazing incidence architectures, like the one shown in the upper image that you can see here. And you have primary, secondary mirror reflecting to a focal plane array. From the X-rays perspective, each of these pairs of mirrors really looks like a very thin annular region, which has a very small collecting area. So you nest many, many shells together. And then to make things so that you're not building meter scale shells that are millimeter thick, that are very, very challenging to handle, you typically will segment these mirrors into many smaller segments. The consequence of this is that to build up square meters of effective collecting area in the X-ray band, in the soft X-ray band, you would need tens of thousands of these components, and they all need to have nanometer scale RMS surface figure accuracy. So this is extremely challenging, especially from an optomechanics perspective. The typical way of the method that has been used for decades now has been to make really, really good optics and then don't screw them up. And the lower image here is from an X-ray probe mission that's currently in phase A development called AXIS. And that is the strategy that is being used here. And it is likely to be successful, at least for their requirements, but not necessarily for a subarc second angular resolution telescope. And so they start with these segments, they assemble them into modules. This is really the crux of the problem. Assembling modules into a telescope is a less significant problem, although it does have significant challenges, of course. So creating a module, you can do this in many ways. There are many ways to build these X-ray mirror modules. There are 4 fundamental process steps that need to occur, they can occur in multiple orders. The key here is that the ones in red here are ones that introduce figure error to these mirrors, and the one in green is the one that fixes the figure error. The current state-of-the-art process is really to do that figuring at the end, make those really nice optics, and then don't screw it up. But what we want to do is do that figuring at the very end of this process so we can fix all of those errors and hopefully don't screw it up after launch. So this is what we call final step figuring. The way that we are working to do this is using a concept called a flex module. And I'll go into the details of this, but let me just start by pointing out where the X-rays are going in and coming out. They're reflecting off of the concave sides of these mirrors, so the downward facing side that you can see here. And there's a primary and a secondary mirror here. And then they reflect to the detector, which is not shown in this image. Everything needs to be built on a relatively stable structure, and this is a representative base structure here. This element here is called a flex segment. This is a flexure supported optical surface. We plan to use ULE for this. Currently, we are using other types of glass for this, and these are relatively small in our current implementation, but we would like to scale these up to be a bit bigger. But they're not huge. I mean, most X-ray telescope mirror segments are not very large. The mirror surface is this smaller section here, and it's on the concave side, again, that we're reflecting off of. They're supported by these things we call realignment beams. These allow us to provide rigid body motions of those mirror surfaces. And then those are connected with small flexures, and I'll explain how we make those a little bit later. Everything is welded together using an ultra-fast laser, and I'll explain how that works in a little bit, or at least I'll show a demonstration of that. The key here, though, is that you need to be able to provide a deterministic way to bend these mirrors after everything is assembled. Otherwise, you can't do this final step figuring. You need to be able to change the shape of the mirrors and the rigid body alignment after everything is assembled. The key process that we've developed in our lab here at the U of A is called ultrafast laser stress figuring. The way that this works is you fire an ultrafast laser into glass materials. This generates stress. You can control that stress through various parameters, and it's highly predictable. And so then this allows you to design stress patterns that deterministically bend your mirrors in a way that allows you to correct the figure errors. It doesn't generate particles. It's all done inside the glass, and it's done in an atmospheric environment. It also does not generate mid-spatial frequency error or roughness, which is a killer for X-ray optics. We've demonstrated that this can achieve something close to the requirements for a subarc second angular resolution telescope on flat surfaces. That's a far cry from doing that on X-ray mirrors, but it's a good start. So the process fundamentally works. This example was on a 100mm diameter, 1mm thick fused silica wafer. We've also done this on materials like ULE and other relevant materials. And we can get down to something like 10 nanometers RMS accuracy in just a few iterations of this process. And the slope errors, which is what's relevant for X-ray mirrors because of the grazing incidence, is on the order of what we would need. We also built a flex module, and this incorporates a few additional processes in addition to that ULSF process. This is all made of fused silica. We made also one out of ULE, although with slightly different geometry. This incorporates two flat flex segments, and this is shown in the image, the upper image that you see here. And you can barely see there are two thin glass mirrors in there. And etched out of those are these flexures that I showed you a couple slides ago. On the left and the right of the module of this square mirror that you see there, you kind of see these rainbow patterns. And that's because we welded those, we used an ultrafast laser to weld those mirrors onto these spacers and onto the mirror below it, and then onto this thick wafer used as the base. We were also able to perform ULSF on this structure. The performance was not quite as good as what we've had with flat wafers, but this is a new geometry for us, and we are still learning how to actually perform this process on this particular geometry. What we have coming up is that that was done on flat surfaces, but we need to do this on curved surfaces. And these surfaces are essentially cylindrical with a small cone angle to them. And so we've developed processes to actually perform a selective laser etching process that we had done on flat surfaces. Now we can do this on curved surfaces. The image on the lower image here was actually a product of an undergrad in my group. One of the main bottlenecks and what we are currently, or what we have proposed for funding from NASA to help alleviate, is that we don't have curved substrates of the required quality with which we can perform all of our process steps that we have developed. And so that's where we are going next. And I just want to wrap up by saying that this final step figuring process, I think, has the potential to give us ultra lightweight, ultra thin precision optics. This is not just for X-ray optics, although there is a very specific need for this in X-ray optics, but you can imagine trying to build very thin optical systems for other wavebands, near infrared, visible, UV. And this could allow you to make these very thin, highly accurate surfaces that are not necessarily, I mean, they can be freeform surfaces, not highly steep freeforms, but they can be freeform surfaces. The three steps that really enable this is the selective laser etching process, ultrafast laser welding, and ultrafast laser stress figuring. And we've developed all of these in our lab in the context of making precision optical systems. So thank you, and I'm happy to answer any questions.
Altering is still the material that you tested exactly narrow necessary materials.
We have tested a wide range of materials, all glass, with the exception of sapphire. So we've done fused silicon ULE. These work great. ULE also can be slumped because it at a reasonable temperature. We've also worked with a few other types of glass, but ULE and fused silica are by far the most effective for the ULSF process. For some of the other processes, other types of glass work fine as well. Sapphire also seems to work great for the ULSF process, but probably less useful with some of the other processes.
How do you measure, you showed some plots of like surface topography, how do you measure that?
We use piezointerferometry. Yeah, that's a great question. So for measuring the actual X-ray mirrors, you need a computer-generated hologram to generate the wavefront that matches the intended surface. In addition, because of the way that we need to access the backside of the mirror, we actually also need to measure it from the backside of the mirror. And this creates a few other nuances that I didn't talk about, but are important to get accurate measurements. Yeah, we would measure it from the backside, create a map of the deformation we want to create, and then we would plug that into our ULSF software to generate the laser recipe that then generates that deformation.
Very quick. Oh, thanks for the great talk. I'm wondering what is the temperature, operation temperature range of these mirrors?
So X-ray telescopes are often operated near room temperature. I have a student who's tested the stability of ULSF at high temperatures up to about 500 C, and it appears to be quite stable. Above that, it degrades.
All right. Thank you.
Thank you.